is a topic that keeps coming back. You're going to do hypothesis testing of the binomial distribution, which is what this is. You're going to do hypothesis testing for the strength of a correlation. In fact, I think that's coming up very shortly. And you're going to do hypothesis testing for the normal distribution. So understanding the concepts behind hypothesis testing in this context is going to really help you going forward. If you have a look at the question, this is the type of question that we're trying to work with, all right? And we will answer this question in a bit. You can see, you can imagine this being a situation that would occur. A theatre company's got 40% of its customers book their tickets through agents. Redesign the website and carries out a survey, and they choose 10 customers at random, and one of the 10 book their tickets through an agent. Yeah, and they're trying to find out if the percentage of customers has decreased or not. Now, it's turning quite a subjective thing into an objective thing. So someone's opinion of what's significant might differ from someone else's opinion of what's significant. And we're going to apply maths to say, right, if it goes beyond this point, then this is significant. So if you look at it, 40% of their customers book through agents, and then from this sample, 1 out of 10, which is only 10%, right? And so basically we're saying, is 10% significantly lower than 40%? Right? That's what we're asking. And the other thing we're going to get into is about levels of significance, which is basically, that's the condition. If it qualifies, then it will be less than 5% when you work out a probability. That's how it works. But in order to do this, we're going to do an experiment, and it is about, are you psychic? Okay, this is it. Are you psychic? Now here's the experiment. I'm going to use a random number generator to generate numbers between 1 and 4. Right? We're going to do this, basically you are going to try to predict what number between 1 and 4 will come out next. We'll do it 20 times. And then we're going to see whether or not the number of times you predicted correctly makes you psychic. Like literally, statistically, significantly psychic. Right? Now, in a sense, it also exposes the weakness in statistics, because I don't believe that anyone's psychic, right? In my opinion. Anyway, right. So let's think about that experiment. Okay, if we were to write it as a random variable, what's the distribution? Okay, 20 repetitions of the experiment, and you are to choose a number between 1 and 4 and write down how many you get right. Can someone describe to me that as a distribution? Yeah. 0.25, yeah, a quarter. Because what we're saying is the probability of success, the probability of you choosing the correct number between 1 and 4, if it's random, should be a quarter, right? Yeah? Right. Now, what we're going to write here, and this is a standard process throughout all of hypothesis testing, we're going to write down what we call a null hypothesis, and we're going to write down what we call an alternate hypothesis. Now, the null hypothesis is a description of there's nothing to see here, everything is fine, everything is as we expect it to be, right? So if we conducted this experiment and there's no such thing as anybody being psychic, then the probability of success is going to be 0.25, isn't it? Right? So that's our null hypothesis. It's like our starting point. We're saying that if you're not psychic, then the probability of success is a quarter. Done. Right? And then we've got this alternate hypothesis, which we call H1. Now, the alternate hypothesis is what happens to this probability if somebody is psychic, right? So what do you reckon? If somebody's psychic, what would happen to the probability of 0.25? Yeah? Okay, if they knew exactly what it would be every single time, it would be 1. But we're saying that they don't necessarily have to get every single one right. They maybe just have to get more than the average right. Yeah. Yeah, we're saying that the probability if you're psychic, is going to be greater than 0.25, right? You're going to get more than that number correct. Make sense? Now, another thing to do at this point, which is really useful, is to think about what you would expect to happen. Now, this isn't part of the specification anymore. It used to be. But we can calculate something called the expected value of x, which is e brackets x. And like I said, it's not on the spec, but it's useful to think about in your head. So if we do this 20 times and there's a probability of a quarter, what would you expect to get? How many would you expect to get right out of 20? Yeah, 5. 20 multiplied by 0.25, right? Makes sense? So e of x is the expected value of x. It's also the mean, it's the average. That's right, it's what would the average person get in this experiment? 5 is what you would expect. So good. Now, this isn't massively part of our calculation, but it's good to have in the back of your head, right? It is just good to have in the back of your head. Anybody want to make a prediction then? How many would it take for someone to get right out of 20 to convince you that they're psychic? 6. So we're going 1 above average automatically qualifies you for being psychic. Does anybody want to be slightly more adventurous with their number? Yeah? 10? Do you think getting 10 out of 10, so getting half right? I think that kind of qualifies, isn't it? It's almost like you're doubling that probability, aren't you? You're taking it from a quarter and saying that it's a half. So actually, if you're getting half right, maybe they'd be psychic. I mean, David's standards are a bit lower than everybody else's, clearly, but that's absolutely fine. So 10. But that's the idea. We're going to come back to that in a minute and see what value actually does. Well, I'm going to impose a significance level, and that's going to control how many you have to get right to be psychic. Okay? Right, let's do the experiment. We've set it up. Let's see how we get on. I'll go to the random number generator. There it is. That's not the first answer, by the way. That was just me checking that it works. So all you've got to do, you can write down on a piece of paper if you want. I just need you to keep a note of how many you get right and how many you get wrong. That's all. All right? And we're going to do this 20 times. So, again, you can do it in your head. You can write it down. I don't mind. But is everybody ready? Okay. So, the first one, make a prediction between 1 and 4. It's a 3. All you have to record is did you get it right or wrong? Right? Right or wrong? Binomial. Right or wrong? Right, make a prediction for the second one. It's a 1. Make a prediction for the third one. It's a 3. Make a prediction for the fourth one. It's a 4. Make a prediction for the fifth one. It's a 1. If you've got all 5 right, you might get the next 15 wrong. If you're average, right? So the sixth one, make a prediction. 3. Make a prediction for the 7th. 2. Make a prediction for the 8th. 4. Make a prediction for the 9th. 2. Make a prediction for the 10th. It's a 3. Someone's already got 6. So David. Wow. Wow. Maybe that's it. I mean, you've qualified for David. You've definitely got at least 6 right. So that was 10. All right. We're halfway through. You can imagine, you know, what are you going to get from the next 10? Are you feeling a bit psychic at this point? Just going so badly. Right. Okay. So number 11. What we got? We got 3. So make a prediction for number 12. It's a 2. Make a prediction for number 13. It's a 3. Prediction for number 14. It's a 3. A prediction for the 15th number. It's 4. So we're 3/4 of the way through now. How are you feeling about being psychic? All right, you feeling confident? All right, so 16, 16th digit. Here we go. It's a 4. Prediction for the 17th. It's a 2. Yes. Prediction for the 18th. It's 4. A prediction for the 19th is 3. And then the final random number, a prediction for the 20th, it's a 1. Brilliant. Right. Before we descend into chaos, compare results, I want you to use that binomial distribution. Okay, because remember it's binomial, you're either right or you're wrong. It's 2 outcomes. The probability of being right is 0.25. The probability of being wrong is 0.75. Can you work out the probability, and say for example I got 6 correct, right? I would say what's the probability of getting greater than or equal to 6 correct, right? And we're going for greater than or equal to because we do need to assess, because the probability of getting exactly 6 correct is very different from getting 6 and above correct. We're looking for like a threshold value. Okay, is 6 any sort of threshold value for being psychic? So calculate your value of your probability, and I'll do for 6. If you've got CG50, then your lower limit is 6. If you've got a class whiz, we're going to do 1 minus the probability that x is less than or equal to 5. I mean, so for mine, if I got 6 correct, the probability of getting 6 or more correct is 0.3828. So there's a 38% chance that you would get 6 or more correct, right? Now, here's where we start to impose a certain condition about what constitutes someone being psychic or not, okay? We're going to introduce what's called a significance level. And the first significance level, well, we'll look at one significance level and we'll see how we get on. I'm going to say that there is a 5% significance level. Now, what that means, well, I'll tell you what, we'll get into what that means after you've analysed whether or not your result was significant. What you're looking for is this. My probability is 0.3828. That is greater than 0.05. 5% written as a decimal is 0.05. That's greater than 0.05. So my result is not significant. Okay, so I'm afraid greater than or equal to 6 isn't significant enough to be qualified as psychic at the 5% significance level. That's the key bit, at a 5% significance level. So I want you to compare your probability with 0.05. If your probability came out bigger than 0.05, I'm afraid you don't qualify as being psychic. If it came out as less than 0.05, you can now walk around and say that you're psychic at the 5% significance level. Did anybody get below 0.05 for their probability? Sam. Just one person. Nice. There you go. How many did you get right? You got 9 right. Right. Can I? Let's just have a look because this is quite important. The probability that x was greater than or equal to 9 came out as what? Yeah, 0.0409. So that is just below the significance level. Interesting. Okay, so only just psychic. Okay, just a little bit psychic. Yeah. Did anybody get 8? Anyway, out of interest, could someone very quickly calculate the probability that x is greater than or equal to 8? So 8 wouldn't have been significant, would it? So actually, this value of 9 is the value that tips you from being not psychic into psychic. All right? If you've got 8 right, you ain't psychic. If you've got 9 right, you're psychic. Okay? We call x equals 9 is called the critical value. All right? It's the point at which the outcome goes from being non-significant to being significant. And x is greater than or equal to 9 is what's called the critical region, which means that any result bigger than or equal to 9 is significant. Without labeling it as the critical region, if somebody got a result of 11, you would have to test the probability of x being greater than or equal to 11 and looking at that probability and comparing it with 0.05. Yeah? If it's less than 0.05, then obviously it's significant. If it's greater than 0.05, it is not significant. But by identifying a critical region, you automatically know that anything greater than or equal to 9 is going to be significant, and it saves you from doing that test every single time. All right? So we've got two things really going on here. There's two different calculations that you're going to be asked to do. One is testing a specific value, like you did with your own value, and comparing it with a significance level. If it's below the significance level, then your result is significant. The second thing that you're going to have to do is you're going to have to find these threshold values, these critical values, to establish whether or not a result is significant. Now, that was at the 5% significance level, okay? We could have had a 10% significance level, right? And at the 10% significance level, it looks like actually 9 is still the critical value, isn't it? Because 8 was 10.2%. Okay? It's not below 10%. So it's still going to be 9. If we had a, could someone test for me, just out of interest, say we had a 1% significance level, all right? Because those are the most common significance levels you'll be working with are 10, 5, and 1. So can somebody find that threshold value for me that would take someone to be psychic at the 1% significance level, would he? 11, is it? So what is the probability that x is greater than 11? Greater than or equal to 11? Okay, so 0.0039, which is indeed less than 1%, and greater than or equal to 10, I'm assuming is going to be bigger than the 1% that we need. All right. So do you see how if we reduce the significance level, it takes more to be psychic? Does that make sense? Okay. Now, this is where I get into what the significance level really means. The significance level you need to think of as being the probability of getting it wrong. So we'll go back to Sam here. We said that Sam was psychic at the 5% significance level. And what we're saying is that there's a 5% chance that we're wrong about that. So it kind of means we're 95% sure that Sam is psychic, right? But that's what the significance level indicates. And you can think about it. If we reduce the significance level, if somebody gets 11 or higher in this experiment, there's only a 1% chance that we're wrong in saying that they're psychic. So they're 99% sure that that person would be psychic, right? Do you see how it all kind of links together? Someone in one of my classes last year, when we were doing the second year singles course, got 12. So that is like, yeah, 99% sure that he's definitely psychic. And then yesterday, in one of my classes, a couple of people got 2. What was the lowest value? Did anybody get lower than 2? Who got 1? You got 1. Wow. What was the probability of getting greater than or equal to 1? I mean, that rounds to 100, right? So this is like there's a 100% chance of getting at least 1 right. But that's cool. That's fine, right? That's just what it is. It's a random variable. It's the outcome of an experiment. Of course, things like that are going to happen, right? Does it mean that someone's psychic? Who knows, right? All we're saying is what the chances are. Right. So that's hypothesis testing, and that's what it's all about. Let's go back to this question that we looked at the beginning. Theatre company, right? 40% of its customers, and then they carried out 10 randomly chosen ones, and they found out that 1 out of 10. So what we're trying to work out is 1 out of 10 significantly lower than 40%. You see what I mean? Okay. So let's set up the question. This is how I would answer it, and I'm going to model this one and then give you a very similar one to do. So I'm going to first of all write down the distribution. We have a binomial distribution because that's what we're working with, and you can see it's success or fail. We've got 40% of the customers book their tickets through agents. That's the known fact. That's the known success rate. The survey is 10 customers. So we've got 10, 0.4. Okay, 10 trials, 10 customers. Probability should be 0.4. Yeah, that's what we're testing. Now, you have to write these null hypotheses and alternate hypotheses. And some questions specify that you must state them clearly, and other questions just expect you to do it without prompting. So H0 is that there's nothing to see here. The probability is 40%. Yeah? It's always going to be. The probability here matches the probability here. The alternate hypothesis, we need to make a decision. In our experiment, it was that it was going to be greater than 0.25. Because we'd expect someone who's psychic to have a higher probability of getting it right. The language in this question, you're looking for those types of words. Is the percentage of customers who book their tickets, has it decreased? All right. And if it doesn't have a word decreased or increased in it, look at the number. 1 out of 10 is less than 40%, isn't it? So we're going to say our alternate hypothesis is actually, do you know what? That probability is lower than 40%. Yeah, and that's what we want to test. We have, again, we have a 5% significance level. It's worth writing that in. Another thing that I'm going to write in that I haven't alluded to yet, but we'll get to, is that this is a one-tailed test. And that means that it uses the word increase or it uses the word decrease. A two-tailed test, which I'll look at in a minute, is where someone would state the probability has changed, but they don't specify greater or lower. Right? So we're looking at a one-tailed test. So we've got our significance level, we've got our hypotheses, we've got our distribution. We are going to test the value, right? And the value comes from this. The result of the survey is that 1 of these 10 customers. So we're going to say, right, what's the probability then that X is less than or equal to 1? Remember, we always have to test the cumulative probability. Right? The probability of getting exactly 1 is very different from the probability of up to and including 1. So we're going to test less than or equal to 1. If you're wondering why it's less than or equal to 1, it's because we're saying that the probability is going to be lower. And so we're looking at that lower side. Effectively follow the pattern. If that's less than, then this is less than or equal to. Somebody work it out for me. What is the probability of X is less than or equal to 1 in this particular distribution? 0.0464. Okay, cool. So we've got 0.0464. What do we do with that number? One thing, only one thing. We compare it with the significance level. And so the next line of your working just says 0.0464. Actually, that's less than 0.05, right? Now, what did we say about psychic people? Their probability had to be less than 0.05, didn't we? That was a significant result. So when your probability is lower than the significance level, that's a significant result. Okay? Now, we're not finished. There's 2 more marks to pick up in the question. One of them comes from a statement of your conclusion without context. And here's the statement. There is sufficient evidence to reject the null hypothesis. Right? It's a significant result. 1 out of 10 is significantly lower than 40% at the 5% significance level. So we have sufficient evidence to reject H0. Okay. Statement 2 is contextual. Right? And we say that there's evidence to suggest, and here's where you use the wording of the question, the percentage of customers who book their tickets through an agent has decreased. Here we go, it's another essay, right? And you have to do this, that the number, quote the question, the number, not number, it's percentage, my apologies, there we go. That the percentage of customers, I mean, I'm already bored of writing the sentence. Right? We're mathematicians, right? We don't do essays. Evidence suggests that the percentage of customers, oh goodness, there's more to come, who book their tickets through an agent has decreased. Don't skimp on your statements. All right? Quote the question. Write down exactly what it is. Now, has anybody noticed how woolly those statements are? How they're kind of non-committal? Yeah? That's what we do. Okay? The quote that was attributed to Mark Twain is 3 types of lies. There's damned lies, and statistics, right? And so with statistics, you can tell any story you want. So what you're basically saying, like, the reason we do this is statisticians get paid by people to write reports on things. And what the statistician is doing by giving those conclusions is, oh, there's enough evidence to reject it. It doesn't mean it's true. I'm not saying it's true. I'm just saying there's evidence to reject it. All right? Pay me. Okay? That's it. And nobody can come back to them and say, you were wrong. They go, no. Read it. I wasn't wrong. I just said that there was no evidence. Pay me. Okay? That's what we do. So you have to be woolly with your statements. Don't go steaming in and go, yeah, it's definitely changed. Don't say that. All right? You're committing then. Just say there's not enough evidence, or just say there is evidence. The other thing I want to draw attention to is it is best practice to talk about whether or not you reject H0. Don't say you're going to accept H1. Now, I'm not saying you're going to get marked down for it. It's just better practice to say whether or not you're rejecting the null hypothesis, because this is all about the null hypothesis. Okay? The whole point of this is that null hypothesis true or not? Can we reject it, or can we not reject it? That's it. Okay, there's a question that's identical that I want you to work through. It shouldn't take too long. I'll pause the recording. I want you to do it. Go. Here we have the answers to that question. You have your distribution 20, 0.15. H0 is that the probability is 0.15. H1 is that it's greater than 0.15. There's a 1% significance level. It's a one-tailed test. You're doing probability of x is greater than or equal to 8, which for class quiz is 1 minus x is less than or equal to 7. Comes out as 0.0059, which is 0.59%, which is less than 1%. That is a significant result. 2 conclusions: sufficient evidence to reject H0, and therefore there's evidence that the proportion of non-smoking customers has increased. Yeah? It's easy, this, right? Tricky. That's fine. This will also be on a video, a very long video, but it will also be on a video. You got a photo? Cool. So here's a slightly different question. Well, I mean, it's different in one respect only. You've got this nutritional expert, children ate healthier in the past, that's what they always say, right? It's measured by a number of kids. Apparently they looked at small goats. They eat 5 portions of fruit and vegetables a day. Proportion that ate 5 a day was 40%. Believes the proportion is lower. So when you're reading through this, you should be starting to formulate in your head what's going on here. Okay, which direction are you going to test your probability? What's the probability of success in this binomial distribution? What's the number of trials? Okay, we're picking out all of those key facts and just turning it into mathematical language. Then part A says, find the critical region. Now this goes back to the psychic experiment. The critical region, remember, was finding the threshold that returns a significant result, right? So we decided that anybody 9 or above was going to be significant. It's exactly this, right? So we've got a 10% significance level this time, and we're going to, level of significance for the expert's belief. So I'm going to let you do this because I think that the psychic experiment is enough to give you the head start that you need on this question. I'll pause the video, I'll do the working, and then I'll talk through what I've done. But have a go, all right? I'll give you, what, 4 minutes or so to do it. All right, so here we have a worked answer that I'm going to talk through. As ever, set your question up at the very beginning. Write down the distribution, B 15.0.4. Write down your null hypothesis, that it's 40%. Write down your alternate hypothesis. This nutritional expert believes that it's lower, so we're going to go P is less than 0.4. 10% significance level is one-tailed, which might not mean anything to you at the minute. The other thing I've calculated here is the expected value. Remember we said in our experiment, how many would you expect to get right out of 25, right? So the number of trials times probability. You would expect there to be 6 children in this sample of 15 if the probability was indeed 40%. And all that's given you is a bit of a starting point for the values that you're going to check, right? And it just saves you a bit of effort. A rule of, just something that I always do, and it's not written down anywhere, but I tend to look at that expected value and then I'll go 2 to the side of it. So if I'm testing lower, the first one I tested was less than or equal to 4. Because if you're around about the expected value, chances are you ain't going to get a probability that's significant because you're around about what's expected. So I started with 4. Less than or equal to 4 came out as 0.2173, and then less than or equal to 3 came out at 0.0905. Yeah, can we check those values? Did we get those? Yeah. Which means that the critical value is 3, and that means that anything less than or equal to 3 is going to return a significant result at the 10% significance level. Now, the actual significance level is interesting. We haven't talked about that before, but hopefully you'll be able to see the actual significance level is 9.05%. Yeah, because that's the probability of less than or equal to 3. Yeah? So we can say that there is 9.05% chance of us making the wrong conclusion from this experiment. Yeah. And then it says complete the test, part C. And what it means there is you look at this, 2 children, and this is what I was saying earlier. Rather than having to go through the process of testing x is less than or equal to 2 to get a probability, because you've worked out the critical region, you can see 2 is less than 3. So it's definitely going to be significant. So therefore we make our 2 conclusions. There's sufficient evidence to reject H0, and there's sufficient evidence, obviously, that the proportion of children who ate 5 a day is lower than in the 1950s. Now, I suddenly realized that the examples we've done so far have all been evidence to reject H0. If you haven't got the evidence, all that happens is you write the same sentence, but you write there's insufficient evidence to reject H0 and insufficient evidence that the proportion. So you see how those 2 statements are effectively the same. It's just that if it's not true, you write insufficient. If it is true, you write sufficient. Done. Boom, bam, boom. So I was going to get you to do this one, but I don't need you to get this one. This is the last bit I'm going to talk about. We've got a whole consolidation lesson tomorrow, so there's lots of time to practice this anyway. But have a look at this question, and I want you to read through it carefully and tell me what the difference is with the ones you've done so far. Did anybody notice the difference? Is there a difference? Fine. Exactly. It doesn't commit to either being lower or higher. Okay? And this is a 2-tailed test. And that's the difference between one-tailed and two-tailed. If there's no implication or statement of increase or decrease or higher or lower, and it just merely goes along the it's different or it's changed, it's a two-tailed test. And here's how you do the difference, all right? First, write your distribution. So we've got a binomial distribution. Percentage, here's the probability is 15, 20 appointments to be monitored. So we've got 20, 0.15, right? That's our distribution. Our H0 is still that the probability is 0.15. Our H1 is the first place that we have a difference. So remember, in the questions you've done so far, if it commented on an increase or higher, you had a probability higher. If it went lower or a decrease, you went lower. In a two-tailed test, if it's just talking about a difference, you just say that the probability is not equal to 0.15. Okay? It might be higher, might be lower, don't know. It's just not equal to it. Now, you have a 10% significance level, but it's a two-tailed test. And what we have to do, because this could be either higher or lower, we're going to have to do a little bit of extra work. And do you remember when I drew the binomial distribution as a picture of a graph earlier on? What we're actually looking at is each side of the graph, the left-hand side and the right-hand side of the graph. And so we're going to take this 10% significance level and split it in two, so that we've got 5% at the right-hand side and 5% at the left-hand side. All right, just kind of see how that works. 5% dedicated to the, if it's bigger than, 5% dedicated to the, if it's smaller than, but 10% overall. Yeah? So we're going to say 5% in each tail. And 5% is the value that we're going to use for comparison. Now, we're looking for the critical region for this test, all right, at this 10% level of significance. And here's where the expected value really kicks in and is useful. We're going to calculate the expected value, 20 multiplied by 0.15, which is what? 3. Expected value is 3. And we're going to pick a couple of values. We're going to pick a number that's smaller than 3, a number that's bigger than 3, and we're going to test both sides. Exactly what we did in the last question, until we get probabilities less than or equal, less than 0.05. Right? So if I start and I want someone to do this for me, what's the probability that x is less than or equal to 1? What's the probability that x is equal to 0 for this distribution? And then maybe somebody else, if you could do what's the probability that x is greater than or equal to 5, and then 6, and then 7, and keep going for as long as we need to. 1.756. Okay, so it's not less than 5%. What's the probability that x is 0? 0.038, which is less than 5%. Yeah, so we've got a value that's less than 5%. Brilliant. What's x is greater than or equal to 5? Okay, kind of similar to that, isn't it? You see how either side of the expected value you're getting similar probabilities. Greater than or equal to 6? Not quite less than 5%. Greater than or equal to 7? Which is less than or equal to 0.5. So we've done both sides of this distribution, haven't we? Yeah? And what we've got then is our critical region for this test is going to be x equals 0, or, there it is again, set notation, love a bit of union, or x is greater than or equal to 7. And so if we then actually tested a value, 0 is significant, and anything bigger than or equal to 7 is significant. And we mean significant enough at the 10% level to say that the probability is different. Right? Part B, so this is our critical region, right? Absolutely. We were looking here for values that were less than our significance level, which is what we're used to. Part B asks a slightly different question again. It says, critical region for the same test, if the probability at rejecting either tail is as close as possible to 5%. Yeah? Okay. So we're doing the same values, these ones over here, but this time we need to be close to 5%. And it doesn't matter if we're over 5%. That's the key difference here. So look at less than or equal to 1 and look at 0. Which one is actually closer to 5%? So that's like 17%, that's 3.8%. Yeah? So 3.8% is closest, agreed? Yeah? So we've still got x equals 0. But what happens up here? Which one's closest to 5% out of these two? It's this one, isn't it? Yeah? 0.0673. So this time, our critical region has actually changed, isn't it? And this is where critical region questions can throw you a bit of a curveball. All you've got to look out for is, what are they asking for? Right? And they will either specify that it has to be as close to the significance level as possible, or they won't mention it. If they don't mention it, you have to go under the significance level. If they do mention it, you have to go as close as possible to the significance level. Follow? Now, if I look back at this part A, you might also be asked for the actual significance level. How do you get the actual significance level for part A out of these two probabilities? Yeah, and you add them together. This is the thing, all right? So we're adding together the two probabilities from each tail. Can someone do that for me quickly? What's 0.0388 plus 0.0219? Which is 6.07%, which is, you know, I'd say considerably under the 10% significance level we were looking for, right? So actually, what we're saying is these two results return a smaller chance of having an incorrect conclusion. What's the actual significance level for part B? Not 0.1061, yeah? So 10.61% chance of being incorrect. And you can see the effect it has, all right? If it's got to be as close to the significance level as possible, 10.61% is a lot closer to 10% than 6.07%. Right? But again, just to kind of reiterate, you only need to do this bit, this part B, if it specifies that it is as close as possible to the significance level. It's a case of RTFQ. Read the full question. Okay. Right. I mean, there's only sort of 15 minutes left, but have a go. All right. Here is a question firmly based on what we've just talked about. So yeah, here we have an answer. Sorry for the scruffy writing. We've got a distribution 300, 0.03. H0 probability is 0.03. H1 is that it's not 0.03. It's a significance level of 5%, which means we've got to split that in half and do 2.5% at each side. The expected value is 3, which isn't massively helpful, I'll admit, in this one because the number of trials is so large. It gives us a decent starting point for our less than or equal to, because less than or equal to 1 comes out at 0.0011. What was less than or equal to 2? Did I get that wrong? Zero. Yeah. There's 0, right? 0, oh no, 3 even comes out. Sorry, video. Welcome back, recording people. Fix the mistake. So the lower tail, x is less than or equal to 3, comes out as 0.0199, which is less than 2.5%. And at the other side, I started off by testing 5 and then realized that that was going to be like 95%. So I just added 10 on. I thought, let's go for 15 and see what happens there. And 15 comes out at 0.0390, and then 16 comes out at 0.0203. So greater than or equal to 16 is a critical region. So we've got less than or equal to 3 or greater than or equal to 16. And the actual significance level comes out when you add those two probabilities together, which is 4.02%. We're done. We are done. Anyone watching the video, thank you for watching 45 minutes worth. I've never talked for that long. Bye.